Thank you for the introduction. It's great to be joining you remotely from Singapore today. So this is work I did with my collaborators Amrit Kumar and Ilya Sergey a couple of years ago while I was working at Zilliqa. And this was published at PLDI last year. So if you're interested in the details, do make sure to check the paper out. Let me give you some intuition about what we are doing. So we are using formal reasoning techniques, as in the previous talks, namely static program analysis first, but not in the usual way, which is to establish correctness or the absence of certain classes of bugs. Rather, we are using static analysis to optimize the execution of smart contracts. So our goal is scalability of the underlying blockchain rather than correctness of the contracts. Secondly, we are using static analysis to enable smart contract sharding. Our analysis is not part of the compiler. So our goal is not to generate, say, better bytecode from some high-level solidity, for instance. But in some sense, our analysis is part of the consensus protocol itself and lets the protocol execute these smart contract transactions in a better way than it otherwise could. I'll explain this in a lot more detail immediately. So the motivation of this work is we want to increase the scalability of blockchain systems. Now, given the audience, I expect you to know this quite well, but to refresh your memory just a little bit, there are two big bottlenecks when it comes to scaling blockchains: state size and transaction execution. So in a typical blockchain system, every node in the system must store the entire state of the system to be able to process transactions, and it must execute every transaction to validate that others are doing it correctly. So this works as far as it goes, but as you know, it doesn't scale very well as the number of transactions increases or as the size of the system state increases. And in particular, with this architecture, adding more nodes to the network does not increase throughput, and it does not allow more state to be stored. So this is already a big problem in practice. I'm not going to go into details. State bloat affects Ethereum and other chains as well. Different chains make different choices in terms of how much they expect from validators in terms of minimum hardware requirements. But the bottom line I want to convey is that in monolithic monolithic blockchain architectures, the transaction execution throughput of your blockchain is limited by the capacity of the least performant node in the network. Well, there are many proposed solutions to these problems, as you know. The one that is relevant for this talk is sharding. And the idea behind sharding is to split the network into subsets of nodes called shards, and then have each of the shards process a subset of the transactions. So this is execution sharding. State sharding also exists, but it's somewhat orthogonal to our work, which is about transaction execution sharding. And there are blockchains that have execution sharding already. The one we built our prototype on top of for this work, Zilliqa, is one of them. But the issue is all of these blockchains take a somewhat naive approach when it comes to sharding smart contracts. Concretely, what they do is they assign contracts to shards, and then every transaction that interacts with the contract is processed by the shard in which the contract lives. So for example, here, any transaction that interacts with this orange contract called MyToken would be processed in shard 1. The issue with this approach, of course, is that if the MyToken contract is very popular for whatever reason, the shard nodes at some point will no longer be able to keep up with the transaction workload. And well, people interacting with other contracts on that shard will have a difficult time. And the problem here is, even though the rest of the network is not doing anything, in this example, the rest of the network has spare capacity, that spare capacity goes unused and shard 1 still gets bottlenecked. So this is the problem we are solving. how can we fully or more fully utilize the network's transaction processing capacity, even in a sharded blockchain architecture with smart contracts. Now, what we would want to do kind of conceptually is we would want to replicate this contract across all the shards and have each of the shards process some of the transactions to evenly split the workload. And of course, we would want the resulting system to behave as if the contract is not sharded at all. We would want to keep sequential semantics for transactions. How could we achieve this? I mean, I'm showing you the picture. Like, what's the problem? The problem is that as far as the consensus protocol of the system is concerned, this smart contract is just a black box. It's a bunch of state with some associated transitions, ways in which the state can change. And it's not clear for the consensus protocol what it would mean to shard this contract. You can't simply clone the contract in each of the shards because that wouldn't behave as if it was a single contract. So what can we do? Well, what we can do is not treat the contracts as black boxes, but have the consensus protocol look at the code of the contract to determine how to split the contract and how to shard transactions touching these contracts. So we're solving this problem of sharding smart contracts, and we're solving it by having the consensus protocol look at the contract code to decide how to shard the contract. So more precisely, the consensus protocol performs static analysis on the code of the contract, and we have two different kinds of analyses to enable sharding. We have ownership analysis, and we have commutativity analysis. And I'll go into details in just a bit. So let's see how this works. The idea is to look at the contract code. Let's kind of look at the contract code. Obviously, this is a very artificial example, so I can show both analysis in with the same example, but it's enough to illustrate the idea. So this is the MyToken contract that we had trouble sharding earlier. And this keeps track of the balances of different people, Alice, Bob, and Charlie. And users interact with this contract by either buying tokens with some external currency, or you can think of this as minting, perhaps, or transferring tokens to one another. So how can we shard this contract? Well, the idea is, rather than keeping the entirety of the contract state in shard 1, we can split its state, that is the user balances in this example, across all 3 shards. So this lets us process independent transactions in different shards, so we don't bottleneck shard 1. In particular, the blockchain can look at the code of the buy tokens or mint transition and determine that the only piece of state it modifies is the balance of the buy. As such, when it sees a transaction from Alice buying tokens, it knows it can process it in Alice's shard 1. Similarly, if Charlie is buying some tokens, his transaction can be processed in shard 3, whereas previously both these transactions would have been processed in shard 1. We can now process these transactions in parallel because the blockchain knows the state used by the transactions is owned by different shards. It belongs to different shards. And what enables this is static analysis and ownership analysis on the contract's code. So we analyze the code of the buy tokens transition to determine which parts of the state it can touch and route transactions to shards based on that information. Okay, that's fairly straightforward. What about more complex transactions? Say we have 2 transactions, one in which Alice transfers 5 tokens to Bob and one in which Charlie transfers 3 tokens to Bob. These transactions are quite clearly not independent. They both change Bob's balance. And moreover, both of these transactions with this sharding scheme we've imposed touch the state of multiple shards. Can we process them in parallel? And in fact, we can process them in parallel. And we can do it because these transactions have commutative effects. Concretely, the effect is to set Alice's balance to 6, set Charlie's balance to 9, and these effects commute because they touch different portions of the state, and add 5 to Bob's balance, and add 3 to Bob's balance. And these effects commute because they express a commutative operation. And looking at things this way, we can see that the order in which we process these transactions does not matter. We can execute them in parallel, as we've done, and merge or join the effects deterministically, and then apply the effects to obtain the final state of the system. And this kind of reasoning is enabled by our commutativity analysis. Okay, so that was a fairly long introduction and motivation, but it was kind of necessary to give the appropriate intuition for what we're doing. So now what I'm going to do is I'm kind of going to restart the talk and show you a lot more of the detail of what we've done and how it works behind the hood, so to speak. So we built our system, CoSplit, on top of the Zilliqa sharded blockchain, which uses the Scilla programming language. Scilla is a programming language inspired by SystemF, specifically designed for writing smart contracts. And it takes inspiration from this theory of communicating automata. So there's a very clear, unlike other languages, in Scilla, there's a very clear separation between computation and communication between contracts. Contracts communicate with each other not by method calls, but by explicit message passing. And that avoids a lot of issues around reentrancy and similar things, and makes contracts somewhat easier to verify. But a lot more importantly for our purposes, Scilla is a very, very simple language. Most computation in Scilla is pure, is non-effectful, functional. And the impure part of the language doesn't have loops or recursion. So this makes Scilla a very, very good target for static analysis and lightweight verification. Our analysis can be quite precise. So this is what Scilla code looks like. It's slightly simplified, but not too much. So this shows a fragment of a fungible token ERC20-like contract. It shows a part of the transfer transition of this contract. So on the top of the slide, there's a declaration of the state of the contract. Usual thing, it's a mapping from addresses to integer balances of tokens. And on the bottom part of the slide, there's a code of the transition that this contract can take. And I want to stress that this really is a transition in the automata sense of the word. It's atomic, there's no reentrancy, and so on. All this code executes in one block, and it changes the state in one block. We're going to look at this code in more detail after the next slide, so there's no need to go through it now. Okay, so the idea of our work is we look at the contract's code and do some static analysis on it to figure out what the contract does. More precisely, we produce what we call an effect summary for every transition in the contract. So this captures an over-approximation of what that transition does, simply put. It captures the components of state that are read and written by the transition, the interaction that contract might have with other contracts, messages it might send. And the effect summary says, for example, things like this transition might read from that field, it may write to a different field, and it may accept some native tokens, for example. This gives us enough information to apply ownership analysis and identify which transactions do not interfere with each other. Commutativity is a lot trickier, and a large part of the paper is about commutativity. I'm not going to go into a whole lot of detail in this talk. To determine, at a high level, to determine which effects commute with each other, we developed a linearity-aware flow-stew analysis. So this is kind of similar with the linearity stuff in Move. but with some data flow added. Kind of similar, not quite the same thing. This is inspired by the cardinality analysis in the Haskell compiler. And this analysis tracks, for example, which reads flow into which writes, but also more generally, which values flow into which other values and how they flow into other values. For example, does this value show up linearly in that other value, or does it contribute in some sort of nonlinear fashion? What operations are applied to this value to obtain that value, and so on. And we express this information as what we call contribution types, which I describe on the next slide. So this is the domain of the analysis, and the contribution types are the bit in the middle. I'm not going to go into detail here. Basically, what we track is cardinality of different sources of reads, basically, into fields that and what operations are applied to these values and what cardinality that value contributes to some other value in. If you want the details, look at the paper, but it really is easiest to understand how this works with an example. So let's take a closer look at the code we've just seen to get an intuition for how this works. So this is the code of the transfer transition of the ERC20-like contract I've shown you earlier. And let's go through this line by line in the same way the analysis does to see how the analysis works on this code. So this is a transition that has its parameters to and amount, and there's this implicit parameter underscore sender, which is the originator of the transaction. And the transition is supposed to transfer tokens from sender to. So the first line there, it reads from this balances mapping at the key sender, and it binds that value to this from bal token. So the effect of this line is reading from balances sender. Then we condition on the value we read. So there's an effect for conditioning on a value. We bind that value to this new binder balance. And here we see that the first contribution type. So this binder bal, the value it has is described by this contribution type. So its value is obtained from the balances sender that flows linearly into bal and with no operations applied to it. Then we condition on balances sender and amount again. We calculate the balance of the recipient of this transfer. We calculate the new balance of the sender of this transfer by subtracting, effectively in the contribution type, the balances sender flows linearly into this new balance with the subtraction operation applied to it. Amount flows linearly into this new from bal binder with the subtraction operation applied to it. We write this value to balances sender, and then we read the balances to, add the amount to it, and write it again. And all these annotations on the right form the effect summary of the transfer transition. And it should be mostly clear what's going on. The analysis kind of goes line by line through the contract and describes what the contract is doing. The tricky bit is the commutativity analysis, or these contribution types, and the detail of how that works is described in the paper. I'm not going to go into it in the talk. Okay, so we have these effect summaries. How do we use these to shard contracts? Well, the idea is we don't have a automated tool to give hints. But there are some guidelines that we have, and they're partly in the paper, some guidelines about how you should be writing your contract so it's shardable. And the analysis itself, so there's a developer-facing tool that tells you why your contract is not shardable. So there is some feedback, yes.
So related to Nina's question, how complete is your commutativity analysis? Is it? Can you explain when it fails? When it or?
It's obviously not complete. Well, it is complete, but sometimes it gives you uninformative type. So I don't know if this is commutative in that sense, but it's sometimes difficult to explain why that is the case. It's mostly when higher order features are used in the pure fragment of Scylla. That makes commutativity analysis quite tricky, and especially the linearity analysis becomes quite tricky when you have higher order functions and maps and folds and that kind of thing. We do give kind of line-by-line summary of the types as we've shown in the slide, so you can kind of see where things go wrong and where the analysis gets confused.
Yeah, I mean, just checking if I understood correctly here. You're inferring those footprints and so on. I forgot how you call them. And
yes,
can the user also specify them ahead of time, or?
Well, no, because this is not quite verification. Well, it would be possible for the user to specify them, but we need to be able to prove them to be able to make use of them, right? Because if the annotations are not correct, then that actually impacts the correctness of the overall consensus protocol. So one limitation of this approach, or risk of this approach, is that the correctness of the static analysis actually impacts the correctness of the consensus protocol itself. That's the downside of integrating it with the consensus protocol.
But maybe it's easier to prove than to infer, right? And also, maybe you could check at runtime that what the user said is correct, and if not, you just trap and you charge them the fee anyway, or something like that, right?
Yes, so I mean, there's definitely the approach of, I guess, proof carrying code, where the contract comes with some proof of how it can be sharded, and the consensus protocol just has a checker. We haven't looked into that.
One more question, please.
Very cool stuff. I just wonder whether you are aware of block STM and related work, because similar ideas which you presented here can be used for parallel execution instead of sharding. No?
Yes, I am aware of it. Yeah, the similar ideas can definitely be used for local parallel execution. So you have a multi-core processing for your blockchain. Actually, there was an intern who worked at Zilliqa after I built this thing, applying the same analysis for local execution. I'm not sure what came out of it, but the same ideas can be used to parallelize things locally on a multi-core processor rather than for sharding.
Let's thank the speaker again.